go through some high level kind of view of kind of Lemna's current technologies, primarily as it relates to the lagoon market and here in Wisconsin. I've put together 5 or 6 different case studies of different facilities here within the state with various treatment requirements, just to give you a sense of what some of the projects are that we've worked in the past with. I'm sure you know the market here and in the Midwest, the primary driver since probably the late 90s has been ammonia removal, primarily in cold applications. I'd say in the last probably dozen years or so, it's been not only that, but phosphorus removal, obviously, as well in these facilities. So I think most of the case studies I pulled together have both some degree of an ammonia limit a year round and then a phosphorus limit as well. There might be one plant in that mix there that doesn't have a phosphorus limit, but most of these plants that I pulled together have a phosphorus limit as well. So to me, it's the easiest way to kind of learn what the technology is about when you see one in action and see a case study and so forth. But we'll go through just kind of a background of what some of our technologies are about and so forth. I've been with the company since 1999. Company was founded in 1982. That image there is of our first really, I'd say, innovative lagoon-based wastewater treatment technology. That was the namesake of our company, our duckweed process. That's what Lemna is. It's the Latin name for the duckweed plant. And that's probably what's the biggest differentiation about our company is we're in the lagoon business first, and then the technologies kind of come secondarily to us. We're not a company that's here's our technology and we're going to find a market or a situation and go focus it on. We've always looked at the lagoon market from a forward-thinking standpoint, and look for technologies that we can adapt to the lagoon-based wastewater market to make it a viable technology for the future. Many of the technology that we developed, in fact, are much of what you'll see here today. We seem to be kind of ahead of the curve with many of our technologies, kind of waiting for the market to come. We see that across the U.S. quite a bit when there's EPA or a state regulatory agency they always say, well, boy, this is going to happen, right? It's right around the corner. Just wait, and then, things get watered down and dragged out and delayed and so forth. And that's just kind of how things go. So yeah, this was one of our first technologies. Since then, we've introduced, a dozen to 20 different technologies into the marketplace, primarily focused on the lagoon-based market. Obviously, here in the Midwest, as I touched on, the primary drivers are ammonia removal and then phosphorus removal, kind of secondarily to that. Kind of breeze through some of these items since we got off to a delayed start here. Some of you guys know all this stuff. We'll focus a little bit about ammonia reduction in the process. Most of you, I'm assuming, have worked, with lagoons, have understand the basic concepts associated with why lagoons tend to not nitrify. Much of the conversation that we have and many folks have relates to temperature and what do you do about cold weather and augmentation of temperature in lagoons. We'll touch on that. But there's a lot of other aspects to nitrification in lagoons that need discussion and addressing as well if we're going to develop a process that can meet the type of treatment requirements that are out there. So other than temperature, we talk a lot about aeration and mixing. You'll see how there's quite a few different approaches to aeration and mixing in these upgraded lagoon plants. Detention time within the lagoons is a big discussion. The adage of more is better is not necessarily the case. We'll shed some light on that. Here in the Midwest, alkalinity isn't necessarily too much of a concern. Having enough of alkalinity in the wastewater to be able to effectively nitrify. I was in New Hampshire this past week and looking at some of our facilities there, and nearly every one of those plants have to augment to some degree alkalinity so they can fully nitrify because of the softness of the water there. So that is a problem depending on where you are in the country. You know, what is dissolved oxygen? What does that play into the process? A little bit on that. And then from an ammonia standpoint, just many times having higher than typical BOD performance, having elevated TSS levels can all have some kind of negative impact on ammonia performance within the lagoon. So back up to that. So we look a little bit about the marketplace and wastewater treatment and what of our experience have been here in Wisconsin. Our first facility that we installed that was really focused on cold weather nitrification, we installed back in 1997 in Brownsville, Wisconsin. And that was really the first plant here in Wisconsin that we introduced our floating cover technology for insulated processes. And that was really our first, the development of that technology as it relates to the rest of our process was really where we discovered the benefits of heat retention in the lagoon system and really setting the stage for nitrification in cold weather climates. Since then I don't know how many facilities we have in the plant around here in Wisconsin, 15 to 20 different plants probably over those years. So there's a pretty good footprint of facilities that have been in the ground since then. Some stuff. Oops. Damn it. So one of the things that come up on existing facilities and a lot of times it's the communication that we start with at the onset with an engineer like yourself is, you're looking at the performance of a lagoon plant and it's it may or may not be meeting the BOD limit. It's probably seasonally meeting the ammonia limit in the summertime, and it may or may not be meeting its other treatment parameters. And many times we start looking at the effluent data, like what's coming out of the plant, and go, oh, well, they need to treat a little better here. They're meeting this limit here. And we're sort of designing from the back of the plant, right? You're trying to improve the effluent. Our philosophy is a little different than that. Let's look at the influent parameters and work on all the objectives, not just fixing the ammonia, but better BOD removal, solids handling, sludge digestion, sludge handling in these lagoons is becoming an ever increasing issue. Maybe not necessarily here in the Midwest where we have lots of land apply, but sludge digestion. What do you do with it? What do you do with solids at the end of the life of these lagoons is an important aspect of it as well. So when we talk about designing based on influent conditions, that's really what we're talking about.
Somebody chime in.
I think that might be Sarah trying to bounce back in.
Is that
It's on my
you want
computer.
to look at it?
Yeah, I don't know if we can see if she's good on the Teams. See if we can log her in. Yeah, I think Kate's controlling that and she stepped away, so we might be go up there. Yep. So clicker. There we go. Now we're good.
Now I hear you guys.
Got you back. Sorry about that.
No problem.
I was just making sure your speaker's maxed out.
Yep.
So, as far as how we go about looking at advancement in lagoons and we look at a specific application, our first foremost goal is always taking advantage of whatever existing infrastructure we have, working within the confines or footprint of an existing lagoon. Sometimes works out great. Sometimes we can make modifications without little distraction to a facility or little, earthwork or civil activity going on within the lagoon. In other applications, digging a new hole in the ground makes more sense. Many of these facilities, when we look at places like Illinois, for instance, Illinois tends to have a pretty strong desire to take unsewered communities and put in a sewer system to get them off of septic tanks. There's a lot of still new plants being constructed, so new lagoons and so forth. Once we take a look at the existing lagoon infrastructure and see what we have to work with, our next goal is to look at the lagoon configuration primarily to improve its hydraulics, get the detention times of the lagoons from a treatment perspective where we want, and then consider aeration and mixing requirements specific to the treatment objectives that we're faced with. Touched a little bit on the idea of heat retention. We'll focus a great deal on that in some of these case studies. It's one of the primary components of our technology is the covered lagoon system, primarily for heat retention to create a stable environment for treatment. And then finally, after we get the lagoon designed from a standpoint of aeration and mixing and hydraulic detention times and so forth, then we take into solids management into consideration. And with the advent of phosphorus removal now in these processes, looking at sludge handling volumes, what to do with solids when the lagoons are full, so on and so forth, become pretty important. So here's a kind of 30,000-foot view of what a Lemna system is all about. Some of the primary components that you'll see in a Lemna system. So the first item we'll draw attention to is really item number 2, the Lemtech modular cover. Mentioned it a couple items before. So when we came up with this technology, it was really, we weren't really thinking of it as a method for heat retention. It was primarily for algae control application. You'll notice that first image I had up of the duckweed plant. Well, duckweed really did 2 things in lagoons. It acted for nutrient uptake. It would take up phosphorus, it would take up nitrogen and so forth, but it also provided a shade cover to the mostly an anaerobic or facultative lagoon. So it would minimize algae growth within the process. And so we were looking for a more mechanical technology for that replacement. Well, we started working with the modular cover technology and realized, boy, it had this great heat retention characteristics, especially if we had insulation to it. So that was really the development of using that technology from a standpoint of retaining temperature within the lagoon. The second item there is the aeration. The aeration philosophy, the scheme, how we go about designing aeration is quite a departure from a traditional 10-state standards aerated lagoon. That'll probably become a little more evident when I share some of the case studies. It's not about what we aerate with, it's kind of the method and philosophy on how we go about aerating lagoons. That's the most, the biggest change that we see. Third item there, Lemna polishing reactor is our fixed film attached growth technology that we use primarily for nitrification, as well as we have a denitrification application for that technology as well. The Lemna polishing reactor, the submerged attached growth technology, has been with our company in the mid-80s. We were using that in combination with our duckweed technology, so it's been around a long time. So polishing reactor, so you'll see a bunch of applications of the reactor. So again, that's our primary device for nitrification in the majority of these applications for post-treatment. And as I mentioned, we have a version of this technology that we're using for denite as well. And then our phosphorus removal process, which is a pretty basic chemical addition and mixing system. And that is shown here between our primary aerated cell and our final settling cell. You'll see a variety of different ways we go about accomplishing that in some of these case studies. Just a little background and detail what some of these technologies are all about. Here's a kind of a breakaway of what the cover is all about. So that the heat retention, the way we go about designing this process is a method that we've developed over the last several years. And so we've developed a pretty good predictive model of determining heat loss in a specific application. So if we know the wastewater temperature coming in, we know the geometry of the lagoon, and we know the ambient condition it's experienced in wherever the town is located and so forth, we can calculate or predict the heat loss in the lagoon down to maybe plus or minus a couple tenths of a degree Celsius. So if we know the influence coming, let's say the influence coming in at say 10 degrees Celsius in the wintertime, and we have a detention time in the lagoon of 20 days, and the lagoons in Green Bay, Wisconsin, so we can look at historical temperature performance. We can size the insulation value of the cover so we have a known effluent coming out of the plant. So that's critical from a design perspective, because now we can design at a much higher wastewater temperature. Instead of 1 degree Celsius, we can design at 7, 8, 9 degrees Celsius. A typical covered lagoon like this will see a temperature loss in the worst time of the year in January of about 1.5 degrees or 2. So it conserves nearly all the temperature with it that's coming into the basin. So if it's coming in at 10 degrees, it's going out 8 degrees Celsius. So that's the temperature we kind of have to work with. Just some design features of it. So it's made from a HDPE outer shell with an insulation sandwich between the two layers of HDPE. It's passive in nature, meaning rainwater and snow melt can drain between the cover panels. Gases like from the aeration can escape between the same cover seams, so you're not, collecting rainwater or snow melt or anything like that, or gas underneath. And then there's an anchoring system that secures the cover to the perimeter, as well as the body sand tubes, which is a system we developed a dozen years or so ago that prevents, wind uplift of the cover under high wind conditions. So here's an application of a cover on a lined lagoon. You'll notice it's recently rained here, so the water's, there's a little bit of pooling here and there, but for the most part, the water's drained off the cover. This application not only used fine bubble diffuse aeration, but had some mechanical mixing in for a different application. Cover can be installed on a lined pond with riprap, grass, clay, whatever the application is from a standpoint of the side slope. Some photographs here that'll show a few more details. A couple of the main key components to point out here, you'll notice the cover panel that's immediately to the right of that mixer is a little different color. That's what we call our walkway panel. So that's a 4-inch panel. It's made from a textured HDPE. It's a little thicker panel. It just makes it nicer for walking out on the cover. You'll notice the aeration lateral is sitting in the cover seam right to the right there, which is right here. So one of the nice features of this is our diffusers are suspended off the lagoon bottom about 1/2 foot. And there's an access panel located here. So there's 4 diffusers on this aeration lateral. So if you wanted to service that diffuser, change out diffuser membranes, operator can walk on the cover, flip that hatch open, retrieve diffuser, slide out new membranes, put a diffuser back down. So it makes getting at equipment a little easier than either a floor mounted system or a system that has a floating lateral and hanging diffusers where you'd have to be out of boat. So operationally, it's got a little bit of an advantage from that perspective. So this is an application with riprap on it. It just shows you a little more close up of what how the cover integrates with the aeration laterals and so forth coming up from the shore. Some guys out on the cover looking at a diffuser, getting ready to pull up a diffuser. That's what that looks like. So this is the polishing reactor. This is a little older view of it, but, so the photo on the left there is a reactor in operation. So that tank is 10 foot of water depth. And the media that's shown on the right is what's in that basin. So that media is our lower density media. We have 3 or 4 different densities of media depending on the application. That configuration is a 6 foot by 8 foot deep bed in a 10 foot reactor tank. And then you'll see each one of those aeration feeder lines feeds a row of coarse bubble diffusers that are sitting underneath each cube. So those modular in nature, those cubes can be pulled out of the tank, reinstalled. Although we don't see a lot of, really any maintenance to the process from that perspective. Some of the benefits of having this fixed film approach is minimal sloughing of that media. We don't have to mix it. We're only aerating the media, so we have quite a bit of less energy, all things considered, in comparison to, say, a moving bed reactor and so forth. It's a one pass-through flow, so we're not recirculating anything here. Flow comes in one end of the basin and out the other end. There's a smaller reactor that's probably a 100,000 gallon a day or so polishing reactor there. Flow comes in the close end there, and then we have a pre-aeration diffuser for mixing in that application, and then flows through four reactor cubes before discharge.
Is normally covered and
Yeah. So this was taken before it was covered. And most of the reason we cover them is really more for algae growth than anything.
Okay.
Just because by that point in time, the water's so clear, you can kind of see right through it. It just, that sunlight, you just get algae growing in there, weeds and stuff. So we tend to cover them.
do you use like same type of?
Yeah, we use our same cover panels on it. So go through a couple different case studies here just to give you a flavor for what this is all about. This is a map I put together to just kind of show some comparative plants of interest. And what I did is we took a climate map that was already developed for climate zones for some application, and put it in colors. And what this really represents is, the green shaded area or the purple shaded area, the blue shaded areas basically represent temperatures that are all relatively similar across the country. So, for instance, if you looked at a facility in Wisconsin that was in blue, and you looked at a plant in Montana or wherever, those would basically represent a very similar winter climate, within 10 degrees or so. So what allows us to kind of do is comparison. If you're like, oh, where do you have a facility in this kind of climate? You kind of look at this map and get a flavor for it. So that's kind of why I put it together. Some of the facilities, so you can see quite a few reference facilities that we have here in the state and so forth. And again, with this is just focused on the cold, so I didn't really show any plants that are in the southern half of the country that we have in operation. So this is the first case study I'll start with. This is in Forest Junction, Wisconsin. So this was upgrade of a seasonal discharge lagoon. Has both ammonia limits and phosphorus limits. I think this probably started up in 2014, 2015 or so. So pretty small flow, only 600 people. Here's a little closer up Google Earth image I took here. So you can sort of see the outline or layout of the old seasonal discharge. They had that large square lagoon on the left, and then the right-hand lagoon was a large rectangle. So obviously with seasonal discharge versus a continuous discharge, we need a heck of a lot less volume. So they built out the 2 process lagoons in the corner of that second facultative seasonal discharge lagoon. So now we have 2 primary treatment lagoons. That first cell operates as a 3-cell aerated lagoon. So cell 1 is a complete mix cell of our baffle curtain. Cell 2 and cell 3 are partial mix lagoons with a baffle wall in between. You'll notice the blower building there south of the first lagoon also has their chemical storage tank for phosphorus removal there. We had a phosphorus in a manhole and there's a flash mixer, basically where you can't see.
Can see that little dot right in the middle.
You can't see the arrow, but you can see it between the,
Yeah.
between the two lagoons there. So we got a chemical addition there. And then we have a baffle curtain that's installed in this settling pond and a floating mixer. We call this our flocculation zone. So we get a little better mixing in here of chemical. And then we use the remainder of this pond for precipitation of our phosphorus chemical. What comes out of there through the polishing reactor discharge and then out. And that's pretty
What do you use the big cells for? Nothing?
nothing. Yeah. That one on the left, I think now is almost dried up now.
Sludge that accumulates in the settling cell, how do you take that out?
Eventually in 15 plus years, it'll have to be dislodged.
Dredged out?
Yeah. They did some sludge profiling there, I think last summer, and they have 2 feet in there now after 10 years or so. Just, I think we sized it for 25 years or something like that. Size that, so. So, just, 60,000 gallon a day flow. So pretty small plant, typical municipal coming in. Effluent objectives of 1.3 and 4.5 winter ammonia and a 1 milligram per liter phosphorus. They tend to adjust their alum. I think they're using pack now. They tend to adjust their pack upwards until they're kind of right around that 1 milligram per liter. They get a little high and stay right at that number. If they wanted to, they could probably meet something quite significantly less, but you'll see their numbers kind of just hover along 1 as they conserve their chemical consumption. Some photographs during and after installation. That I think that first photo there on the left was during the install. So we hadn't installed the aeration laterals yet. So normally the cover gets installed first and then all the aeration and baffles will get installed from the surface of the cover. So they're assembling the diffusers and they'll drop them down through the patches of the cover, close the cover back up and so forth. So that's where that first photo was taken. That's looking back from the effluent of the aeration pond towards the influent. And the guys out on the cover doing, I think they're installing the first baffle photo. The second photo is after the aeration laterals were installed and all the piping's in play. See the blower building and the chemical storage tank there. And then the third photo is of the settling pond. And you can see the polishing reactor there in the background.
Can the covers take like a big 24-inch heavy wet snow?
So it's just a matter of displacement and how much buoyancy or what thickness of cover we have. If you have enough snow, you'll get push down on the cover and then the snow will melt.
Yeah.
There's enough heat loss through the cover that over a few weeks, if you have a snowfall and after a couple of weeks, that snow will slowly melt off and drain through there. Okay, see, the worst part of the winter, that snow will stick around a little longer. If it's a spring or fall snow, then. Just some data. It's hard to look at these graphs. I could shoot you all sorts of data from these plants if you want to take a look at it. The typical trend that you will see in most of these plants from a standpoint of BOD removal is there isn't a seasonality from a BOD removal. Most lagoons, BOD removal is great in the summer. The numbers kind of creep up in the winter and drop back down in the summer. If there's a turnover of the lagoon, it usually will have an effect. With the cover on the system, we don't have a turnover on the lagoon, and you don't have the temperature variability from a standpoint of BOD removal. So the BODs pretty much stays really consistent. For instance, in Illinois, most of our facilities in Illinois have to meet a 10 CBOD limit, and you can meet a 10 CBOD limit without issue with this technology on a continuous basis. Same thing goes for the solids removal, since we're not growing algae in this process and everything's covered. Any TSS excursions really isn't an issue. Lagoons aren't turning over, so you don't have a TSS rebound from a standpoint of that, generating solids and so forth. So TSS performance tends to be extremely good in these plants, and this is early on and kind of startup. Once these facilities get acclimated from a nitrification standpoint, there tends to be very little variability as far as ammonia removal. There's either many times a disruption in performance, but it's either nitrifying or it isn't. And that's what we tend to see at most of these plants. Next plant here, similar name, similar location. This is in Forestville. This is sort of up in Door County area. It's probably about the same size, a few less people, but I think the flow is pretty darn close. This is more of an application, that last application was basically brand new construction, even though they built it within the confines of that lagoons, that's representative of a clean sheet of paper, basically, building a new plant. This is a little more representative of a plant that used the existing volume that the plant had and was able to get by with very little civil or, dirt moving at that plant. This facility had two lagoons, a smaller rectangle with the corner cut off, and then that large rectangle at the bottom. Obviously, one of the primary benefits of this technology is because we're treating BOD at a higher kinetic rate from a temperature perspective, and many of our facilities incorporate our complete mixed reaction kinetics in the front of the plant. The volume requirement of this technology is much less than an open air partial mixed lagoon. So, which tends to mean we need much less volume from a standpoint of aeration detention time. So this is a pretty typical application where they had two lagoons. We really only need that primary lagoon for treatment. So they kept that other basin to use as high flow events, emergency. But primarily all the influent comes through the covered 3-cell aerated lagoon before going through the polishing reactor. So that covered lagoon is a complete mix, partial mix, settling pond before flowing into the polishing reactor that you can see there and just north of the lagoon there and south of the building, and chlorine disinfection and discharge there. This plant does not have a phosphorus limit. So their ammonia limits were basically the same as Forest Junction. Flows 57,000 gallons, so wasn't much smaller. Shows just kind of layout of the aeration, 2-cell aeration, aerated settling pond. Most of our facilities have aerated settling ponds nowadays. We've learned a lot about solids digestion in these processes, and we get much better solids digestion and storage capacity in the settling ponds by aerating those. So you'll see a couple of diffusers in that application. Polishing reactor is a pre-aeration diffuser, and then 4-cube reactor before going out to the effluent. This is just ammonia load coming into the plant. Ammonia load prior to the reactor and effluent. This was when the plant was kind of first 4 years of the plant starting up. This was just a study we did of TSS loading and ammonia to demonstrate the media's almost all of our reactors are right at the downstream, so we don't typically settle after the reactor. So this was a study to demonstrate that we could put a reactor there. We don't have a significant sloughing or buildup of the media that would require secondary clarification step after the reactor. So we conducted a study at this facility to do a comparison of TSS performance versus ammonia loading to see if there was any correlation between the two. So this is next one is a little bigger facility. I would put this in the category of sort of a retrofit, but by the time they were done with the plant, it might as well have been new construction from the ground up. A much larger facility, talking population of almost 4,000. This is more of a traditional partial mix kinetic design here from a lagoon perspective. That was primarily an energy decision there. They were trying to get by with as little amount of horsepower as they could, so that gave us the best kind of scenario for that. Primary driver here again was similar to the others, ammonia limits, as well as a phosphorus limit. And as we tend to go up in our design flows, we tend to design in a little more operational flexibility to the processes. You know, on these smaller flows, you can get by with single lagoon or maybe two lagoons, but as we go up in flows, we tend to add some operational flexibility to the configuration of these plants. So here's the design conditions here. Our targets were 15 BOD in solids, 1 milligram per liter of ammonia, and 1 phosphorus. The 3 lagoon facility. Each lagoon, the first 2 lagoons are basically 2-cell partial mix lagoon in each lagoon. So that pond 1 on the what would be considered to the north is a 2-cell partial mix. The second pond is a 2-cell partial mix. We have our chemical addition at between the second cell and the third cell, and then we have an L-shaped baffle in that third pond where we're doing our flocculation mixing, and we have basically the remainder of that pond for solids storage and settling prior to the polishing reactor and discharge. So again, very similar to the other facilities, just on a little larger scale based on the flow. This was a Google Earth image taken during construction, so they had it's labeled completely mixed up, but that's incorrect. They had the first 2 lagoons online. This is before they were doing phosphorus removal. So they were just using those first 2 lagoons, followed by the polishing reactor to accomplish treatment. They had all sorts of liner failures with the settling pond. So this plant was started up and unstarted up numerous times through construction. So it was kind of a nightmare, but it finally got fully serviceable about a year ago or so. So it's a pretty new plant. They have, we talk about operational flexibility. We have all sorts of flexibility in the blowers. So those 3 blowers that are shown there are just for the lagoons. And the way they're piped, they can move the air around a bunch. Plus they have VFDs on all those lagoons, blowers. So there's all sorts of things going on there. The polishing reactor, the photo was taken during construction, so there's tons of foaming going on because it had a huge load going to it, but we'll see that today. But it's kind of a weird image. You'll see the covers on that lagoon, on the tank as well. And that image of that cover is pond 1, so that's the further north pond. So and phosphorus, the chemical storage is in that primary building. You can see on the northeast of the ponds, first image. So January of 21 is when they really got into their final startup after all the starts and stops of that third lagoon. So this is effluent BOD, a few numbers of that. This is basically their TSS when you look at that the January, end of July, January timeframe is when the plant was finally functional. Same with ammonia, it's between that July and January period when the plant's operational. That's the most kind of recent installation that we have that's up and running, and we have a plant in Thorpe that's in construction here this summer. That's will be the next plant going in the ground.
Yeah, that's a big float there, right?
Yeah, it's big, a little bigger than Koshkonong, just under 1 million gallons. Largest facility we've done to date. We did a plant in Poplar Bluff, Missouri, probably 5-6 years ago or so now. That was a 10 MGD plant.
That's a good point. Yeah.
So smallest we've done to date is probably 10,000 gallons a day, and that's the biggest plant we've done here domestically. Is that the sign flow of 10 and a peak flow of 17. But they had an existing lagoon plant. They were used to writing the electricity bill for 5 200 horsepower blowers, and when you looked at the cost of, they upgraded that 10 MGD plant for about $15 million. So you think about what a mechanical plant would have cost that. You know, we couldn't touch it. So you could write a lot of electricity bills for a long time for the savings of the plant, you know. So, this last one here, Village of Wittenberg. I'm sure you guys know what Wittenberg is off of 29 there. This upgrade was really twofold. One, it was the increased industrial load with the meat packer, the casino, and so forth. And they had it. They were getting an ammonia limit as well as a phosphorus limit here. But the primary driver really was trying to get extra capacity out of this lagoon plant. So this facility has an extremely small footprint as it relates to hydraulic retention time through the lagoon system itself. The pond one there has a total HRT at design flow of less than 5 days. Same with the second cell. So very high rate, highly aerated and mixed lagoon process here. That first cell operates a complete mix. The second cell can operate in complete mix conditions, partial mix, and then we have this really small detention time settling pond. It only has 2 days of detention time. So when they constructed this lagoon, knowing that solids, you know, like in any process, you know, there's really 2 questions: solids, you want to leave them or forget it, or do you want to handle them every day? You know, those are really your 2 choices. And so the approach here was, boy, we don't have enough volume to treat it every day. So what else can we do? So this lagoon, basically, that settling pond basically tapers down to a cone. And so they created a homemade kind of stealing well in the bottom of this lagoon, and they have the influent pipe come right to the bottom of the center of the lagoon, and then they draw off the top. So all the solids get collected in this little square in the bottom of the lagoon, and they ran some pipe down the side slope of that. And then usually once a year, they'll pump the solids into those reed beds that they have north of plant, and that's where their solids have gone for the last 15 plus years or so. Their ammonia limits here are high enough that we can get the nitrification that we need in the lagoons without a reactor. So this plant doesn't have a reactor. And their phosphorus was added sort of after the plant was upgraded. And I don't really have a good handle on what that looks like right now. But, you know, they've are down on that road. So this is a different application where they have a little higher ammonia limit that we can get by meeting it in a complete mix scenario with a cover without a polishing reactor. And they tend to do pretty good here. This plant's been in the ground, I would say 2006 or 7, if I had to guess. I don't remember exactly, but it's been around a long time. Plant, so forth. winter time. It shows some snow on that. See, it recently snowed there, so you can see this, I must have went on the cover, as you see my footprints all on the cover. It's not real good to walk out there when there's snow on it. You don't know where you're going, but. So yeah, their flows are creeping up to their design condition here. You know, they see a lot of daily max flows at their design condition, so. This is, you know, an extremely aggressive from a hydraulic retention time lagoon, and, you know, they put out a pretty decent affluent given the challenge they have from a detention standpoint. When the floating cover technology was first developed, and there really wasn't a market for it at the time, you know, there wasn't a lot of states that were heavily in the ammonia limits, especially in the northern climates. And one of the primary applications we had for that technology was in really applications where we were out of hydraulic capacity, where we could use the cover to augment temperature, make modifications to the aeration system to get a lot more throughput of treatment out of our very small footprint. With that, I'll open it up to questions you guys have, or.
You'd mentioned, I believe on the polishing reactor side of things, that there was an option to do denitrification.
Yep.
How does that work?
So primarily we'll do that with a carbon addition on a second stage after the nitrification step.
Okay.
So it's non-recirculation. So that configuration is great for smaller flows. It's something you probably don't want to tackle if it's a 1 MGD plant, but that's the configuration. And then downstream of that, you know, will depend on what we're trying to meet from a total nitrogen standpoint and what else we have to meet from a BOD level standpoint. We'll maybe use another lagoon to just partially aerate for settling and clean up any BOD or too much carbon addition. Most of the ones that we do with carbon addition, we may pace off a flow, but we're not putting a bunch of controls in the system. You know, it's kind of put carbon to it and step away from it, because these lagoon operators don't kind of know how to operate it. So you need to have some way to kind of buffer that issue at the end.
Okay.
So usually what we'll do is an aerated lagoon, nitrification, denite, and then if they got another lagoon, we use that kind of an aerated settling lagoon to kind of clean up the BOD and get rid of any additional carbon at the end of that.
So it's okay.
And the idea there is really kind of keeping the lagoon mentality. You know, they're not making a process decision. We're not doing recirculation. Carbon addition's pretty straightforward. You know, we just use micro C in those applications.
What do you
Micro
use?
C.
Oh,
Yeah.
Okay. You don't bypass raw wastewater around or anything?
No. For larger, if we're looking at a larger plant, we'll look at applications like that, but we'll tend to still have some sort of carbon addition as a makeup. And the reason for that is most of these plants, when we get into design, they're so under capacity at startup, you can't tend to produce enough recycle for them, because solid separation is so hard in the lagoon process, you know.
You show phosphorus removal in the very first slide.
Yeah.
Is that an add-on filter then, what that you do there?
Sorry, I didn't explain that very well.
That's, if it's like an add-on process.
Yeah, so when we talk about what we do for phosphorus removal, let's see if I can find it. So our sum total of equipment for phosphorus removal is basically chemical feed skid with or something. Pump in here, a tank, mixer, a diffuser, a manhole, and then a settling zone.
Okay.
With that equipment, we can get you to a point, 0.5 milligram per liter.
Okay.
We have to meet lower than obviously filtration after the polishing reactor would be the next step.
Mm-hmm.
But we can handle all the binding up of the phosphorus from chemical injection standpoint within the lagoon itself. Then it's just a matter of separation after that.